In this video, we're going to discuss induction, continuing on with some more examples, and specifically, we're going to discuss examples that look at fractals. Now, if you've never heard of the word fractal, it just means a shape that keeps repeating in a certain pattern over and over and over. There's all kinds of really neat fractals out there, and we're going to talk about a couple of them today. So the first one is called the Koch snowflake. So how does the Koch snowflake get built? Well, we start with an equilateral triangle, and then we form the next shape from the equilateral triangle by taking every line in the triangle and growing an equilateral triangle in the middle of that line, right in the middle. And then we remove the bottom, so we get this type of shape here. So as a result, these fractals start looking like the following. So we have these shapes. We first start with the triangle, and then notice each line in the triangle is also represented in the next picture, but each one of those lines has an equilateral triangle growing in the middle of it. And then going one step further, that happens again. So each line, like this line right here, is right there with this equilateral triangle that's grown in the middle of it. And you can see it eventually starts to look like a snowflake. So as we were looking at before, it said K1 is the equilateral triangle, and then the second shape in this sequence is this star type shape, and then afterwards it starts to look like a snowflake. A really fascinating thought about the Koch snowflake is if you keep taking this snowflake and getting K4, getting K5, getting K6, so on and so on and so on, you end up with a shape that has an infinite perimeter. So if you try to calculate all the way around, calculate the length all the way around the perimeter, it's infinite. So the limit of this sequence produces an infinite perimeter. However, the area does not keep growing and growing and growing. The area inside of the Koch snowflake, it might grow slightly, but it does tend to a finite area. So you have a finite area, but you can't trace your way all the way around it because the perimeter is infinite. Quite fascinating. So our first job for this problem is to write down a recurrence relation for AN that will represent the number of line segments in KN. So to start us off, A1 is 3. Right? So in this picture, there's 3 line segments. In the next picture, A2 is 12. See if you can pause the video for a moment and try to think about how many line segments are in K3 without actually counting them. Try to think about it. So in K3, there is 4 times as many line segments as in K2. So notice every line segment in A2 became 4 line segments. So we would get A3 as 4 times 12. Okay, so we're ready to write down a recurrence relation for this problem. So A sub n is equal to 4A sub n minus 1. And remember, every time we write down a recurrence relation, we want to state an initial condition with that. So we're just going to formally state that A sub 1 is 3. That's the initial condition that gets the ball rolling in this sequence of 3, 12, 48, and so on and so on. Okay, now we're going to use induction. So you may have tried to solve recurrence relations before by just trying to guess at what the pattern is. Just trying to take the numbers 3, 12, 48, and try to guess at what type of formula you would get out of that. So a wonderful thing that induction can do is verify that a guess is correct. So the guess is that an has another form in its solution as this. So the statement that we have is that a sub n equals that expression for integers bigger than or equal to 1. That's our statement. To be convenient for induction, let's define our statement. I always like to write p sub n for the proposition at hand, and then a colon to represent that that's our statement being defined as p sub n. So let's just take a moment to time out here. P sub n represents either something that is true or false. A sub n represents one of the numbers in the sequence. The colon is defining a true or false statement. So we use a colon to define the statement, and equality tells us that the number on the left and the right is the same. So one thing that we don't really want to write is something like p sub n equals 5. That doesn't make a heck of a lot of sense because p sub n is something that is true or false. 5 is a number. We don't want to compare a true or false variable to a number. So even though they're both letters, and they're both variables, they're variables representing different things. So we'll just erase that off of our screen here and move forward with our problem. So we want to start out with a base case. So we'll start off trying to show that our statement works when we plug in 1. So show p sub 1 is true. So how are we going to do that? We'll just plug in the number 1. So a sub 1 equals 3 from above. There was 3 line segments in the triangle. And we want to verify that that equals 3 times 4 to the power of 1 minus 1. That would be 3 times 4 to the power of 0. And indeed, we get 3 out of the deal. So the base case checks out, and we can say, therefore, p sub 1 is true. So now we are ready to move along to our inductive step. So in the inductive step, again, we'll write down what we want to show. We want to show that p sub n implies p sub n plus 1 for all integers bigger than or equal to 1. And I'm going to start by writing down our goal for our inductive step. We need to make sure that when we replace n with n plus 1 in the expressions from above, the left-hand side is in fact the same as the right-hand side. And we get to use p sub n to help us out because it's an implication that we're showing. We're not showing that p sub n is true directly. We're showing that when p sub n is true, p sub n plus 1 is also true. So a sub n plus 1 needs to be shown to be the same thing as 3 times 4 to the power of n. Okay, now a sub n plus 1, one thing that we can do is use the recurrence relation from part A. So part A tells us, we've already proven or verified to ourselves that this recurrence relation works. In the A sequence, it represents 4 times the previous number. And now we have a sub n sitting there for us, and we can apply p sub n to that, right? P sub n says that a sub n is equal to this. So let's make that exchange. So a sub n is going to get exchanged for 3 times 4 to the power n minus 1. So 3 times 4 to the power n minus 1, and we'll bring along the 4 from the previous part. And now, lo and behold, if we combine our 4s, we do get what we want. 3 times 4 to the power n The inductive step checks out. We'll give it the nice red check mark and write down a conclusion to our induction. Therefore, p sub n plus 1 is true. And this verifies both parts of the induction and verifies the solution to this recurrence relation is in fact correct. Okay, let's move on to the next example. So our next example is on another sequence of shapes that keeps growing more triangles. This grid below is called a corner deficient triangle. Notice in each of the grids, there is a corner of the grid that is shaded out or missing. Each of the triangles has 4 to the power n subtriangles. So this one has 4 to the power 0 subtriangles. There's just one of them. This one has 4 to the power 1 subtriangles. There's 1, 2, 3, 4. And if we break up the third case, there is 4 to the power 2 subtriangles. There would be 16 of these subtriangles in there. Okay, so what are we supposed to do with these corner deficient grids? We're supposed to show that the following statement is true. A corner deficient grid of 4 to the power n triangles can be tiled with trapezoidal tiles made of 3 triangles, just like that. Now we can shift these trapezoidal shapes by rotating them if you like. You could reflect them, but that doesn't really change too much. Rotate them any direction you like and try to fit them into the shapes from above so that they're tiled. Now let's remember what that word tiled means. Tiled means that everything is filled in. There's no gaps or overlaps. We get a nice fit for this repeated use of the trapezoidal style shape. Okay, so I'll solve the middle picture above. That one is fairly straightforward to solve. There is just one trapezoidal shape right there, and we can just identify it and fill in that so it's tiled. I'm going to notate that by putting a little half circle type shape because it's kind of hard to trace out the trapezoidal shape as we go through this process. So our job is not to go through and specifically tile each one of these grids, but to prove that all of them can be tiled by induction. So let's give this a try. We're going to start out with a base case. In our base case, we need to show that the 4 to the power 0 case is tiled. So in our base case, n is equal to 0. That means we have 4 to the power 0, or one triangle, with the corner missing. Okay, and when the corner is missing, there's only one shape there. It is already tiled. So the base case is basically done for us. One triangle with the corner missing looks like this, and it is tiled. Okay, so the base case checks out. We can move on to the inductive step. In our inductive step, we would like to show that p sub n implies p sub n plus 1 for all n values bigger than or equal to 0. So let's remind ourselves what that means. It means that if we can tile the 4 to the power n corner deficient grid, then we can also tile the 4 to the power n plus 1 corner deficient grid. Okay, so let's give this a try. We're going to write down what our goal is and then try to tackle our goal. So we want to consider the 4 to the power n plus 1 corner deficient triangle. Let's write that down. there's my triangle. In this triangle, there are 4 to the power n plus 1 triangles. And one of them is right at the top there, and it's missing. It's been shaded away. Okay, so what would the strategy be to try to tile the rest of this triangular grid? Well, if you were just doing a direct proof and you didn't have anywhere to begin, I guess you'd have to start by just shoving in trapezoidal shapes and seeing if you could fill it up. But of course, we're trying to do this for n in general, and that wouldn't really work because you'd have to continually do that over and over and over for all n values. But in this method of proof, we know that p sub n can give us a proper tiling of 4 to the power n triangles. Maybe not 4 to the power n plus 1 triangles, but definitely 4 to the power n triangles. So is there a way to split this triangle up so that you would see part of it with 4 to the power n triangles? Try to think about that. Pause the video for a moment. Okay, so one thing you could do is draw a straight line across right there and draw it so you would see 4 to the power n triangles in that top part. And now that top part can be tiled by p sub n. There's a little bit of a question, well, what do we still do about the rest of it here? Well, you can also make 4 to the power n sub-triangular sections there by placing, say, an upside down triangle in our triangular grid. Now, there is a little bit of a problem still. P sub n doesn't tell us directly that these 3 subsections can be tiled. It tells us that the top one can be tiled because we're only talking about when the corner is missing. So how could we deal with that issue? How could we help these sections along, these 3 at the bottom, so they are corner deficient? I'll let you pause the video and think about that for a moment. Okay, so the idea is if we place one trapezoidal shape right at the bottom in the middle here, then we force all 3 of those triangular shapes to be deficient. So we can shade in those little areas. And now all 4 of those triangular shapes are 4 to the n deficient grids. So let's write down our conclusion. What we want to write down is that by placing one trapezoid as shown, each of the 4 sections can be tiled by p sub n. And that concludes our induction. So the inductive step gets the check mark, the base case worked out. So therefore, by induction, all of these triangular grids with the corner missing can be tiled with the trapezoidal shape. Now, moreover, we did the induction, we proved theoretically that this is possible, but this also gave us a method to doing the actual tiling. So let's scroll back up to where we were before. Let's take a look and let's try to follow the method that we just came up with to show this domino effect that we proved. So the domino effect is that if we can solve the problem for the first triangular grid, then we can solve it for the second one, and then we can solve it for the third one, and so on and so on and so on. So how does this solution right here help us get the solution right there? Well, what we have to do is follow the steps that we did below in the inductive process and think about our guidelines that we gave ourselves. The first thing that we did is try to see in the 16 triangles that are here, 4 triangles at a time by drawing that triangle in the middle. And then we placed one trapezoidal shape right at the bottom in the middle part to make all 4 of the triangular subsections deficient subsections. And now we can individually tile those by placing in one trapezoidal shape in the exact same way we did in the previous step. Let's try to do this one more time. Let's see if we can step up to the 4 to the power 3 scenario. So we'll scroll all the way down. There's one more problem for us to finish off today. We're going to use what we just did to come up with a proper tiling of a 4 to the power 3 grid. Okay, so the first thing that we want to do is separate this grid into sections that have 16 triangles at a time. So there's my first sectioning. Okay, so next we'll slip in a trapezoidal shape in the middle bottom part of our grid. So now what we have is reduced our problem into 4 copies of the above problem. We just have to repeat all of the steps that we did above 4 times. So let's do that now. What we did above is we wrote in a triangle to separate it into 4 sub-triangles, and then we slipped in one in the bottom middle part. So we'll do that 4 times. We drew a triangle in the middle, and then the bottom middle part gets that trapezoidal shape. And then for the 3rd time, we drew in a sub-triangle, and then the bottom middle part gets the trapezoidal shape. And then finally, the one in the middle, we have our sub-triangle right there, separating the bigger triangle into 4 smaller triangles, and then slipping one in the bottom middle part. And now what we're left with is solving the original problem at the beginning of this section, this example, where we just had a triangle with 4 smaller triangles in it, and it's deficient. So it's really clear where our trapezoidal shape goes in each of these cases. We just have to look at all these triangles and fill in that trapezoidal shape. And again, I'm going to do this with these half circle shapes because it's very hard to indicate where the trapezoid is going in any other sort of pattern. But you can see we complete our entire tiling with this systematic process that the inductive method gave us. Thanks so much for listening. We'll see you on the next video.